I think I miss using the board more than the mass though. This is an upgrade. So before I was using like an old janky ass iPad. And so I bought this recently. So this has been really nice, but I do miss this board.
Hey, Professor, so as like we progress through school, like years coming forward, are we still gonna have like hybrid meetings available, or is that just gonna go away with the pandemic?
You mean next year?
Yeah.
I think it'll be on a faculty per faculty basis. I probably will continue having hybrid stuff. But it's going to depend on the faculty and what they decide. They're probably going to discuss this summer to see if we want to have any university-wide policy, but probably most likely every professor is going to do what they want.
Like Mr. Parks has, it's only almost in person at this point. If you do it online, you don't get like half the information because it's
Because he's on the board. Right?
Yeah, he's on the board.
What's up?
There's a problem that we have to find.
Let me answer. So let me answer Nick's question first. Because he was first. Let me write down the learning objective and then I'll.
We got number 4.
I believe it's for each eye. No, it was number 3.
Then there's this one. This one is.
Yeah. Mine's slightly different. but not too bad. Like, that's number 4 that I have. My value is like my decimal.
Yes. Once every 10 minutes. Mom.
So that's finding part 4. Okay. Convection. Inside, outside, and the distance of a here. Yep.
Always values.
Got that. Okay. And I took the temperature inside. Celsius. Yep. Minus the negative 20 on the atmosphere. Yep. I got it.
Yeah.
Yeah. I mean, still 5. Almost as if like
And right now.
So what? So I have to.
that's your.
Like that.
Trade or whatever. Oh, wait.
All this looks good. It all looks right. Same, all the numbers here are correct. Getting something that's 10 or magnitude 10.
I didn't mean to choose.
No, I mean, you don't, there's no cosine sine. I would need to go back and check, because I'm not sure if I completed this. Well, maybe it's not right. Yeah, let me go back, send me an email. Just send me this,
All right.
just send me a, hour when I go back. And I'll go back.
Okay. I can do that. Yes.
What?
What's up?
And that's why. Yes. So you have. Yep.
I guess.
What do you have?
For the window. Yeah, you would base, you're basically doing the same process twice. You have external convection. It's kind of a.
I like water.
Can't really turn.
Yeah, same process you follow for although I think one of them is diameter, the other is. Make sure you're using the right. Yeah, so make sure you're using the right.
Then you have to add. Oh, I got it. One half. I because there's a little like.
Oh, what's up?
I guess I just somehow forgot a zero.
Oh.
Like I just recalculated the resistance and it's that.
Okay, I see.
I might have just forgot to multiply by 10 or just something weird like that, and it just didn't carry over.
I see. Okay.
That works out.
Nice, okay, that's good.
I'd say that's a hot sauce. Now I think we like, if you like responding. Because we did that.
It's not just. So it's minus.
But you have to know what you start with. You have to know which section. And you're giving us. So for us, we're giving. It's completely possible. And this correlates to which transmission ratio. So for us, it's this, so it's important. UTR has there. This is not about system. This one. Yeah, so look at the graph. Like first look at the system.
Oh.
I thought it was number having.
Oh, you went to Grasshopper number 4? Okay, okay.
I don't know if it's the same.
It should be the same. I mean, there's only one dude, so it should be the same number. What class is 335 in? Is that kinematics? Okay, oh, interesting. Okay. I guess you can tell me if it's the same one.
His number.
I see.
It's the shortest one for turbulent.
I see. Okay. I see. This is definitely not nowhere near that. So maybe it's the same guy, but he did different stuff. All right, it's 2:30, so let's go and get started. All right, good afternoon, everyone. It's our last meeting before spring break. And so after today, you won't see me for 10 days. So it's exciting. So how's everyone doing today? Tired, stressed? Yeah, I know. It's that time of the semester, you know, especially I know a lot of you are probably looking for internships or looking for jobs at this point. So it's tough. And so, you know, it's definitely not an easy time. But at least, you know, at least for this class, you know, once you turn in the homework on Friday, you know, you're not gonna have to think about it until after the spring break. So hopefully that gives you a little bit of a break. Okay, so the plan for today is we're going to continue on with convection, and so we're kind of right in the thick of it. And so we're going to finish up our lecture notes on internal convection today, and then we're going to start our next topic on free convection. Okay. I usually don't like to do this. I don't like to kind of start something and then have it go over the break, but it just kind of worked out this way with the timing. And so, you know, and so after the spring break, I'll do a little bit of review just to make sure that we all remember, because, you know, I kind of don't want today to be kind of like a dead day either. Okay? No. All right. So, go ahead. So remember, homework 4 is due this Friday, and so I know a lot of you guys are working on it. So I've gotten a lot of questions. And so if you are having any troubles with it, you know, please let me know, and I'm happy to help you. All right, and so are there any questions I can answer before we get started? Okay, all right, so let's go ahead and get rolling. Okay, so we're right in the middle of our lecture notes on internal convection. And in particular, you know, our unit is called internal force convection, and that term will have a bit more context once we get to the later point today. Okay. And so far, you know, we've discussed a lot about this idea of the mean temperature, right? And so under this context, you know, when we have internal flow, and so in other words, we have a flow of some fluid that's flowing inside a bound surface. So, you know, most of the time we're considering like a pipe. Okay. And if you have heat that's coming into this fluid, right? Because it's such a finite amount of fluid, right? It's not like an infinite abyss, or it's not like a reservoir. You know, any heat that flows into or out of this pipe is going to affect the temperature of the fluid, right? And so what we're saying is that if you flow in this direction, or if you follow the flow along the center line of the pipe, okay, we call this the z direction. What we say is that the mean temperature as a function of z, this is going to vary, right? And so it's not going to be the same temperature as before, right? Or in other words, you know, if we measure the mean temperature at the beginning versus the mean temperature at the end, most likely these are going to be different because because heat's flowing in and out, right? And remember, we came up with 2 situations where, you know, we could actually solve for this mean temperature, right? And so one such situation was when the heat flux from the wall is constant. Right? And that gave us one expression for Tm of z. Right? In particular, we got a linear function. I'm not going to write down the function again, but you know, it's important to kind of remember what kind of function it is. And we also talked about how we have a situation where the wall is a constant temperature, right? And so this led to a exponential function, or decaying exponential. Right, so those are the two main situations that you have to remember. Okay, And I think the last thing we talked about last Wednesday was that, it's often really hard to fit any kind of real life situation into one of these two, because there's always going to be, the real life is always going to kind of exist between these two. But a lot of times you can make a reasonable assumption whether, you're fitting into one situation or the other. Okay. And so that's the mean temperature. Now let's kind of bring this back to kind of the general discussion of convection, where remember the whole reason we're embarking on this entire unit is so that we can have ways to compute convection coefficients. Right? And we haven't yet talked about that for internal convection. Okay. And so today we're going to answer the question of, how are we going to compute convection coefficients for internal flow? Okay. Because now we're going to kind of move past the situations where I kind of just give these to you. And so now you're going to be responsible for kind of computing these on your own. All right, so the way that we do this is actually the same as what we did before. And so we're going to make use of the Nusselt number. Okay. So remember, the Nusselt number is equal to the convection coefficient multiplied by some length divided by the thermal conductivity of the fluid. Right? Right, and so we're going to make use of this, just like we always have. And if you remember from external convection, and if you've been working on the homework, the way that we compute the Nusselt number is through some kind of equation. Okay? Okay. And usually that equation involves the Reynolds number to some degree, and the Prandtl number to some degree, and usually some other coefficient, right? And so in other words, it depends very strongly on the flow. Okay. So for internal convection, it's still the same. And so we're still going to make use of the Nusselt number. The only difference is that our Nusselt number is not going to have some complicated equation. Okay. Right. I think I mentioned it briefly last time, but for internal flow, what we have is our Nusselt number is simply just going to be a constant. Okay. And so thankfully, that simplifies things quite a bit. Okay. Oh, it's only a constant if the flow is laminar. We'll talk about turbulence later. But if you have laminar flow, finding the convection coefficient is very, very, very easy. It's so easy that you will get upset, and I promise you about that. Okay, so that was just kind of a recap from last time. So are there any questions on any of this? Okay. All right, so let's go ahead and find out what this constant is for our internal convection. All right, and so just like our mean temperature, we're going to look at two different situations. Okay. And so first, let's look at a situation for constant wall flux. So just like our first condition for TM. Okay. And so for constant wall flux, our Nusselt number will always equal 4.36. Right. So that's the case when we have constant wall flux, but we have constant wall temperature, right? So the wall is a constant temperature. Then what we have is Nusselt number is equal to 3.66. That's it. That's all. That's all that we need to know for Nusselt number, right? I told you, it's so simple that it's kind of insulting, especially all the work that we kind of just did up to this point. Right? But even though these expressions are simple, we can use them in exactly the same way as we did before. So let's go ahead and do an example to kind of illustrate that. Very quick example. Okay. And so if you remember from last time, we did an example where we looked at a water heater, right? And we computed the convection coefficient using the surface temperature as well as some of the fluid properties. And so let's take that same problem and let's compute the Nusselt number. Let's compute the convection coefficient using these Nusselt numbers here. Okay? Okay. And so in order to do this, we need the properties of water. Okay. And just like we did in that previous problem, we're going to evaluate them at 40 degrees C. Okay. And so if you want to look these properties up in the book, it's table 8.6. Okay. But of course, you can just use an online calculator, kind of just as we do. Okay. And so if you do that, the thermal conductivity of water is the only one that we need is 630 times 10 to the minus 3 watts per meter Kelvin. Okay. And if you recall from that problem, we had a situation where our wall flux was constant. Okay. And so since our wall flux is constant, we're going to use our Nusselt number up there to be 4.36. Okay. And so what we have is Nusselt number is equal to 4.36, which is equal to the convection coefficient multiplied by the diameter of the pipe divided by the thermal conductivity. And so if we solve this expression for H, we get H is equal to 4.36 multiplied by KF divided by D. Okay. And I forgot what the diameter was. Go back and see. And so the diameter for this pipe is, diameter of the pipe is 20 millimeters. Okay. So that's from the previous example. And so if we plug in that, that diameter, we plug in that thermal conductivity, what we get is a convection coefficient of 137.34 watts per meter squared Kelvin. Okay. Okay. That's it. We didn't even have to scroll. It all fits under one page here, which is that awesome. All right. Any questions on this? Okay. All right. But you're probably like, wait a minute. If I know some of you are kind of looking back in your notes, you're like, wait a minute. When we did the last problem, okay. Remember, the last time we did this example, we computed H using Newton's law of cooling, right? And when we computed using Newton's law of cooling, we got a very different number for H. We got H was equal to 1,500 watts per meter squared Kelvin, right? And so how can these two be so different, right? Neither of these methods are wrong per se, right? So remember last time we used Newton's law of cooling, which is, we've been using it this entire class, and so that can't be wrong. And this new one here, it uses the Nusselt number, which we've used in the previous chapter, so that can't be wrong. And so what's going on? Why do we have such a big difference between the two? Okay. remember, the simple Nusselt numbers that I have up here, those are only valid for laminar flow. Okay. And so when you have turbulent flow, you have to, you're going to have to use a different expression. So, we'll go over that expression later today, but just kind of make note of it. And so in this problem here, when we use the simple Nusselt number, we skip quite a few steps, right? So remember, usually when you do these kinds of problems, one of the first things you do is you compute the Reynolds number to see if the flow is laminar or turbulent, right? And so we kind of skip that step. And so, we got so excited, or I guess I got so excited by the fact our Nusselt numbers are so simple that I didn't check those things. Okay. And so you need to make sure that when you're computing these convection coefficients, that you're using the right correlation based on the whole situation, right? First of all, make sure that you're using the right geometry, but also make sure that you're using the right expression for either laminar or turbulent flow. Okay. Any questions on this? Okay, so let's do another example. So this one's really cool because this one's actually pretty closely related to a lot of the research that I've done in the past. All right, so let's look at blood flow. Okay. In particular, let's look at blood flow in your blood vessels, or let's say inside your arteries. I think we're gonna do capillaries too. Yeah. Inside your arteries and capillaries. An artery is just one of your blood vessels, and so the vessels you can kind of see going through your hand. That's an artery. Your capillary is a much smaller blood vessel.
Arteries are the ones that carry clean blood, right? And then veins carry blood.
I think that's what most people say, but arteries actually carry blood away from your heart, and then veins carry blood back to your heart. And so generally speaking, arteries have more oxygen. They're more pure just because they're taking it away from the heart. Yeah. Mm-hmm. Okay. And so when most people think of blood, they probably think of a lot of biology, right? But I think what a lot of people don't realize is that your cardiovascular system, the blood that's flowing through your body, that's actually your main way of regulating temperature inside your body too, right? So the human body is it's a fascinating thing, but a lot of the processes that happen in your body, like the synthesizing of energy, all that stuff, all of those are very tightly temperature dependent. And so, if your body's not regulated at the right temperature, a lot of things just kind of get out of whack inside your body. And so the main way that your body regulates temperature is through your blood, right? Because your blood, think of it as like coolant that's kind of flowing through your body, right? And so it's the only thing that really kind of flows all throughout. And so your body uses that fluid to kind of transfer heat from one portion to another. Okay? And so their blood, I think a lot of people don't think about it, but it's the main way that your body regulates its temperature. Okay? Basically, yeah. And blood properties are not that different from water too. And so, yeah. Okay, so here's a typical blood vessel. And so we have blood that's coming in. Right, we're going to say the blood has a certain velocity, UM. Okay. We have the mean temperature at the inlet. We'll call that TMI. And we have the mean temperature at the outlet. That was weird. TMO. Okay. We have the diameter of the blood vessel. Okay. And surrounding your blood vessels is what's known as tissue. Okay. Tissue is kind of a broad term, and so, but it's basically human flesh. That's what's surrounding your blood vessels. Okay. And what we're going to say is that the tissue is at a constant temperature, and we'll call that TT. Okay. And so, for this situation that we're going to be considering, we basically are assuming that the wall temperature is going to be constant. All right. And so what we're interested in computing given this situation, right, we're going to assume that the tissue temperature is either hotter or cooler than the fluid. Okay, so the tissue temperature is not matching the fluid temperature. Okay, and so by the time the fluid flows from TMI to TMO, right, the blood temperature will get closer to the tissue temperature. Right. Because if you remember, our graph for constant wall temperature was that of a decaying exponential, right? And so as you flowed along the vessel, then the temperature of the fluid starts to match the tissue, the wall temperature, a lot more closely. Okay? And so what we're interested in computing is, we want to compute the length of blood vessel that's necessary blood vessel that's needed so that the mean temperature of the blood such that the mean temperature of the blood gets within 5% of the tissue temperature. Okay. And we're going to do this under two situations. And so we're going to do it for a typical artery. Okay. So an artery is one of the bigger blood vessels in your body. Okay. Same size as a vein, yeah. Although veins, for veins, the flow goes a little bit slower in the veins. Right, and we're also going to look at the capillary. So a capillary is one of the smallest blood vessels in your body, if not the smallest. And that's when those are the locations where your blood kind of offloads oxygen to or from either a muscle or to your lungs. Okay. All right, so both of these situations are going to have a certain diameter. And so a typical artery diameter is about 3 millimeters. Okay. And for your capillaries, the typical diameter is about 0.008 millimeters. Okay. They also have different flow conditions. And so your large artery will have a mean velocity of about 130 millimeters per second. While in the capillaries, they have much slower flow at 0.7 millimeters per second. Okay. So that's the situation. Any questions on any of this? Okay. All right. And so let's go ahead and run through the whole process, right? So first thing we'll note first we have to note our geometry. And so of course, we are in internal flow. Okay, so that's our flow geometry. Okay. Next, we'll compute the Reynolds number. Okay. Just to check whether we're laminar or turbulent. Okay. And so we're going to do this in both cases. And so I'll call the artery, I'll call that case 1, and I'll call the capillary case 2. Okay. And so for case 1, we have Reynolds number. Reynolds number based on the diameter is equal to rho um times diameter divided by the viscosity. Okay. And silly me, I forgot to give you the fluid properties. And so let's assume the fluid properties are, we have a density of 993 kilograms per meter cubed. Our dynamic viscosity is 695 times 10 to the minus 6 Newtons second per meter square. Our thermal capacity is 4178 joules per kilogram K. Our thermal conductivity is 0.628 watts per meter Kelvin, and our Prandtl number is 4.62. Sorry about that. Got too excited and I skipped ahead in the problem. So interestingly, if you compare these properties to water properties, you'll see that they're very close. And so blood is very close to water. I know there's a popular phrase that blood is thicker than water, which is true, but it's not that much thicker. So it's basically the same as water. Okay, and so you plug in the numbers for the Reynolds number for the large artery, and what you get is 557. Okay. And since this 557 is less than 2300, 2300 being the cutoff for turbulent flow, then we are laminar. So that's great. It does, yep. There are certain locations where it does have turbulent flow, but those are only in places like around the heart. But usually as you get further away from the heart, most of the flow turns pretty laminar. Yeah.
Is it like a combined flow that was like we previously discussed? Like where it's like laminar and then it turns turbulence with you like that combined?
There's most of the turbulence that happens in your blood occurs due to geometry more so than the velocity. And so you have these things in your blood vessels called valves. And so those kind of open and close. And so that kind of naturally kind of swirls the flow. And so you get like turbulent flow like that, but very soon it turns laminar right after. It's very interesting. It's one of the most blood flow. I mean, I'm biased, of course, but blood flow is one of the most complex and interesting flows out there, but it's almost purely laminar. And so usually when you think of fluid mechanics and you think of situations that are really interesting and complex, you think of very turbulent flow. But blood flow has a lot of complexity without having to go turbulent, which makes it really interesting to study. All right, so let's do the same thing for the capillaries. And so the capillaries, we have a much slower speed and a much lower diameter. And so of course, we're gonna have a much lower Reynolds number. And so in fact, the Reynolds number is actually 0.008. Okay. And so this is very much less than 2300. And so we are laminar in both cases. Okay. All right, so the next thing that we're going to compute, now that we have the Reynolds numbers, is we're going to compute the Nusselt numbers. Okay? And since we have a constant surface temperature and we have laminar flow, then we know our Nusselt numbers here is going to be 3.66. Right? Our Nusselt number is just a constant, and so let's go ahead and compute the convection coefficient for the artery. Okay, so our convection coefficient here is going to be 3.66 multiplied by the thermal conductivity divided by the diameter. Okay. And we plug in the numbers for this, we get 703.36 watts per meter square Kelvin. Okay. And for the capillaries, we have 3.66 multiplied by the thermal conductivity divided by the diameter of the capillaries. Okay. And here we get a much larger number because the diameter is so small in the capillaries. And so we get 287.310 watts per meter square Kelvin. Okay. So now that we have the convection coefficients, we are ready to use our mean temperature formula. Okay. Okay. And we're going to use the one for constant wall temperature. Okay. Because remember, what we're looking for in this problem is a length. And so the only formula that really gives us a length is the mean temperature formula. Okay. Because the mean temperature formula is a function of z, and so it's a function of the length of whatever type that we're looking at. And so any problems that involve length, we have to use the mean temperature formula for that. Okay. All right, so let me go ahead and write down the general formula. And so the general formula for this is Tm of z is equal to Tm at O minus Ts times exponential minus pH divided by m dot Cp times z plus Ts. So that's just the general formula for mean temperature for a constant wall temperature case. Okay. And so we have to plug in some expressions for this. And so first, let's plug in for the perimeter. Okay, so we have perimeter P. This is equal to pi times the diameter of the vessel. Okay. The other quantity that we haven't been given yet is the mass flow rate. Okay. But mass flow rate is very easy to compute because we have the mean velocity. And so if we take the mean velocity, we multiply it by the cross-sectional area of the vessel, and then we multiply that by the density. Okay. That'll give us our mass flow rate. Okay. Where of course cross-sectional area here is just pi over 4 times the diameter squared. Okay. And so, of course, those quantities are going to have different values depending on when we're dealing with the arteries versus the capillaries. And so I'll just kind of leave them as those expressions. Okay? But what's more important is that we kind of work through this. We work through the math of this expression. Okay? All right. So the first thing I'm going to do is I'm going to isolate the exponential term. Okay. Because what we want to solve for eventually is this z, right? Because that z will tell us, what length of vessel do we need in order to solve this. Let's solve for this. All right, so let's go ahead and subtract Ts from both sides, and we'll divide both sides by Tm0 minus Ts. Okay, and so we have Tm of z minus Ts divided by Tm of 0 minus Ts. Okay. This is equal to exponential minus pH divided by m dot Cp multiplied by z. Okay. This entire expression on the left right here, we'll set that equal to 0.05. Okay. Because remember, we were looking for a situation when the mean temperature of the fluid is within 5% of the tissue temperature. Okay. And so the tissue temperature here is Ts, right? And so the Ts, we can replace this with Tt. Okay. And if the mean temperature at some location Z, if that is 5%, and the bottom here is 1, so we're saying that between the entrance and the exit, the fluid temperature is within 5% of the surface, then this entire expression right here will turn into 0.05. Okay, and so by setting that equal to 0.05, we cancel out a lot of what's on this left, and we can actually solve this expression for C. Okay. So that's why in this problem, I didn't give you any temperature because we're doing everything relatively, right? And so if we think of like relatively, how close the fluid temperature is to the wall, then we can use that to eliminate a lot of the temperatures in our system. Okay. All right, so now with the left-hand side equal to 0.05, let's go ahead and take the natural logarithm of this. Okay. So you have natural logarithm of 0.05 is equal to minus pH divided by m dot Cp multiplied by z. Okay. And so from here, it's just kind of simple arithmetic. And so we're going to move m dot Cp, multiply that on both sides, divide both sides by minus pH. Okay. And that's going to give us z. Okay. And so if we're solving for z, okay, what we get is z for the artery. This is equal to 8.7 meters. And then the z for the capillary is equal to 3.3 times 10 to the minus 7 meters. Okay. So we have very different answers. So 8.7 meters might seem like a really long distance, right? 8.7 meters is like what? That's like 40 feet, right? Almost around there. And so, if it takes 40 feet of blood vessel to reach a certain temperature, that might seem really inefficient, right? Because if you look at a typical person, or if you look at me, I'm a very short person. And so, I definitely don't have 8.7 meters of length in me, right? I wish that maybe people would like me more if I was taller. But that seems like a really long number. But, and this is outside of heat transfer, but, this is just fun trivia, just like I love blood flow. And so what if I told you that inside your body, you have about 60,000 kilometers of blood vessel inside you? It's just all really tightly wound up into inside. Yes, yeah. And so it's not, you don't just have one blood vessel that flows from your head to your toes. And so, you have, thousands and thousands and thousands of kilometers. They're all just kind of very tightly wound up and kind of stuffed inside the person. So it's interesting. And so if you took the average person and you took all their blood vessels, I mean, this would be really gross, but, just imagine, and you kind of lay their blood vessels kind of, end to end, you probably get something close to like 60,000, 80,000 kilometers worth of blood vessels, which is really creepy, but also really cool at the same time. Okay, any questions on this example here? Okay, I do have one more example, just because this is kind of one way that we can use the mean temperature equation, but you can also use the mean temperature equation to solve for H as well, okay? And so for situations where, you're either given all the information that you can use for this, or if you're not sure if the Nusselt number is correct, then this is another way to solve for the convection coefficient. Okay. Because if you look at our mean temperature equation that we had above, then H shows up there. And so of course in this problem we solve for H first and we plugged it in. But we can do kind of the reverse as well. And so we can use the same formula to compute for H. And the nice thing about this method is that this works, no matter if you're having laminar flow or turbulent flow. Okay. But unfortunately, it only works in situations when you have constant wall temperature. Because if you look at our equation for constant wall flux, then the H kind of cancels out from that equation. Okay, but let's see how we can actually do this, because this is kind of a nice way to solve for H as well. You know, whether it's laminar or turbulent. Okay? And so we have a very simple example here. So we have flow of water through a tube. Okay. And so the geometrical parameters of the tube. Here's our tube. We're going to say the length of the tube is 6 meters. Okay. And the diameter of the tube is going to be 50 millimeters. Okay. The mass flow rate is equal to 0.25 kilograms per second. Okay. And so this is usually a big hint. And so, you know, if you're given both the inlet and the outlet temperatures, that's usually a good hint that you can use the mean temperature equation to compute the convection coefficient. Okay. And so the inlet temperature, so TMI, the inlet temperature is 15 degrees C. Okay. And the outlet temperature, TMO, this is 57 degrees C. Okay. And so, since we are given inlet and outlet temperatures, we can use the mean temperature equation to compute H. Okay. And we're going to do exactly that here. All right, any questions on the setup for this problem? Okay. All right, so let's go ahead and do this. Okay. All right. Oh, and let's assume that we have constant wall temperature. Okay. And let's assume that temperature is, let's note it down. Let's assume TS is equal to 100 degrees C. Okay. So we have a very hot tube. And we're also going to assume that we know the thermal capacity of the water is 4178 joules per kilogram Kelvin. Okay. All right. And so there's our situation. And so let's go ahead and write down our mean temperature formula for a constant surface temperature. We have Tm of Z is equal to Tm at 0 minus Ts times exponential minus P times H divided by m dot Cp times Z, okay, plus TS. Okay, so we're going to make a lot of substitutions into this formula, because the only thing that shouldn't be known should be the convection coefficient. Okay. All right, so for Tm0, we're going to plug in. Remember, this is the mean temperature at the inlet of our pipe, and so we're going to set this equal to Tmi. Okay. This Tmz, this is the mean temperature at the outlet of our pipe, and so we're going to set this equal to Tmo. Because we're going to assume that we're only looking at this section of pipe right here that's 6 meters long. Okay. TS, we already know. TS we know is 100 degrees C, so we can just plug in straight for that. Okay. And the only other thing that's not straightforward is Z. And for Z, we're going to plug in the length of the pipe, which is L. Okay. Okay. And so let's go ahead and start working on this. Okay. And so let's solve for H. Okay. And so first thing we're going to do is we're going to isolate the exponential term. And so let's go ahead and subtract TS from both sides and divide by that quantity there. And so we have TM O minus TS divided by TM I minus TS is equal to exponential minus P times H divided by M dot CP times L. Okay. And of course, the perimeter is just pi times the diameter. Okay. And so to solve for this, we need to take the natural logarithm of both sides. And so let's take the ln. Okay. And so we have ln of Tm O minus Ts divided by Tm I minus Ts is equal to minus pH divided by M dot Cp times L. And so from here, it's just algebra. And so I'm going to take this, multiply on both sides. So this kind of shows up on top. These quantities, P and L, they're going to show up on the bottom because they're up top here. And so if we plug in all the numbers for that, okay, we plug in all the numbers, we get H is equal to 755 watts per meter square Kelvin. So a fairly short example here, but I did want to show you a case where you can take the mean temperature equation for situations when you have the inlet temperature and outlet temperature given to you. You can use that information to solve for H. Okay. And so for internal convection, for internal convection, you're not just limited to the Nusselt number, but if you can use the mean temperature equation here, that can be another method to solve for H in these situations. Okay? And these are typically a bit more accurate than the Nusselt number, because the Nusselt number kind of makes a little bit more assumptions. But for the mean temperature equation, if you can use this one, this usually gives you a better estimate. Okay, and this works whether your flow is laminar or turbulent. And so that's the next part. All right. Any questions on this example? Okay. All right. So let's talk about turbulence really quick. Okay. And so just like an external flow, having turbulence in internal flow will enhance your heat transfer, right? And so it'll make it more than before. Unfortunately, it makes things very complicated because what you have is what's called a turbulent boundary layer. So those are very difficult to analyze. But we do have one correlation that we can use. Okay? And so the Nusselt correlation actually looks very similar to our external convection. Okay. And so the Nusselt number based on the diameter is equal to 0.023 times the Reynolds number based on the diameter, based on the 4/5 power. Okay. I tried to fix it, but it made it worse. 4/5. Okay. Times Prandtl number to the n. All right, so once again, you see that 4/5 power. And so that 4/5 power is pretty, I'd say pretty standard with turbulence, right? And so when you have turbulence, the heat transfer basically goes as Reynolds number to the 4/5, okay? Whether that's internal or external. And so this is our Nusselt correlation. When the Reynolds number is greater than 2300, okay? Because that gives you turbulent flow and internal flow, okay? And you're probably wondering about that n variable. So the n variable can either be 0.4 if the wall is hotter than the fluid, okay? And so if your surface temperature is hotter than your fluid temperature, or in other words, heat is coming into the fluid, then the n is going to equal 0.4. In the other situation, n is going to equal 0.3. So it's going to be 0.3 if Ts is less than Tn. Okay. Right. And so in other words, when your fluid is being heated up, your n is equal to 0.4. When your fluid is being cooled down, then your n is equal to 0.3. And so if you have a turbulent flow in your internal convection and you can't use the mean temperature formula, then this is the correlation that you're going to use to solve for the convection coefficient. All right, any questions on this? Yeah. For heat transfer considerations, we consider 2300 for turbulence. Yeah. Mhm. I've heard of that threshold before too, but 2300 is the one we use for. Yeah, yeah. So, but basically, we say once it hits transition, then that produces kind of a chaotic flow that enhances turbulence. So, yeah. Mhm. Okay, all right. So that's it for internal convection. And so let's go ahead and move on to the next area of convection, which I think is one of the more interesting ones, is called free convection. And so if you notice, when we talk about external convection, internal convection, I've always used the qualifier forced, right? We have external forced convection, internal forced convection, okay? And so the forced in those situations refers to the fact that, we're kind of forcing the fluid to flow, okay? And so up until this point, the fluid flow, or in other words, the fluid velocity, has been caused by some external force. Okay? In other words, there's something that's kind of driving the flow. And so in external convection, we have a lot of the situations we covered were like wind patterns, right? And so wind patterns are caused by differences in pressure in the atmosphere, right? And internal flow, we have flow that's kind of forced by some pressure gradient. So usually we have some kind of pump. For the cardiovascular example, we have the heart that's kind of pumping the blood. And so we have some external force that's kind of adding energy to the flow and forcing it to go, okay? All right. And so let me give you a thought experiment. Okay? And so in the absence of these forces, is it possible that we still get convection? Remember, the way that we defined convection was that convection is just anytime you have heat transfer that's going to a flowing fluid, right? And so in other words, the fluid has to be moving in order for us to have convection. Because if the fluid was completely still, then we just have conduction, right? And so is it possible, and so without anything that's kind of forcing the fluid to move, is it possible to still get convection? And so of course, you know, the answer is yes. That's kind of why I kind of posed the question. It's because it's a rhetorical one. You know, and so the question is, you know, how can we get flow without something that's forcing it to happen? Well, you know, fluids have this property called density, right? I'm sure everyone's probably heard of the saying that hot air rises, right? That's how a hot air balloon works, right? And so for a hot air balloon, you heat up the fluid inside you heat up the air inside the balloon, and that causes the balloon to go up because the hot air inside the balloon goes up. Okay. Even though that's kind of the observable thing that you see, you know, the reason that we say hot air rises is that as you heat up a fluid, its density goes down, right? Wait a second. Becomes lighter. Yep. Okay. And so let's think about that hot air balloon, right? And so for the hot air balloon, you know, yes, we're heating up the fluid. And so, yeah, we're applying fire to the fluid to warm it, you know, but we're not really forcing it to go, right? We're not putting a fan in there, you know, we're not putting a pump on the air, right? And so we're not physically pushing the fluid, you know, as a fan would do or as a pump would do. All we're doing is just heating it up, right? And so just by simply heating up the fluid, you know, that's enough to cause it to move, okay? And so we can leverage this thing, this phenomenon in convection as well, okay? And so what we can say is that if you have differences in density within a fluid, okay, these differences in density can cause the fluid to move. And we have a term for this. Okay. And the term that we use to kind of denote this fact that, you know, we can manipulate the density of a fluid to make it move or to do certain things is called buoyancy. Okay. So let me kind of give you a situation here. So let's say that we have two plates. Okay. What's going on over there? Some like apocalyptic Nightmare Before Christmas thing going on. All right, so let's say we have two plates, and on the bottom plate, we're heating up. So let's say that we have a hot plate on the bottom. And so, you know, we can put some numbers on this. So let's say that our bottom plate temperature here is 80 degrees C, okay? Meanwhile, on the top, we have a cold plate. And so let's say that our surface temperature here will be 20 degrees C, okay? Those are just some random numbers. Okay, so what's going to happen here? And so as the plate kind of heats the fluid on the bottom, you know, we have no other flow otherwise, right? So we have nothing here that's forcing the fluid to move, okay? But we are heating it up. And so what's going to happen is that on the bottom here, you have fluid that's less dense. Okay? Because it's being heated up, so its density is less than before. Okay. And on the top, you're going to have fluid that's more dense, right? Because it's being cooled down. And so in other words, you have something heavy over something light, right? And so that's not a stable situation. So what they're going to want to do is they're going to want to swap places, right? And so the less dense fluid is going to want to come to the top, okay? Because of gravity, right? We're going to assume gravity is in this direction. Okay. Meanwhile, the more dense fluid is going to want to fall down, right? Because it's more dense. And so gravity is going to want to pull it down. Okay. Okay. But as the more dense fluid falls to the bottom, then it's going to be heated up by the bottom plate, and then it's going to go back up to the top, right? And so you kind of have this cycle of fluid where, you know, fluid heats up, it rises up, then it cools down, and it comes back down. Okay. Right. You know, but what do you notice here, right? You should notice here that we do have a movement of fluid, right? So we have fluid that's going up and it's coming down. It's going up, and it's coming down, right? And so just by definition of this, just by definition of the fact that we have fluid that's moving, and obviously we have heat transfer that's occurring through the fluid, you know, this by definition is convection. Right? We have heat transfer to a moving fluid. It's just that the way that we achieve movement is different, right? So we achieve movement through density, not through any kind of forcing. Okay. And so whenever you have convection that occurs due to density differences in the fluid, we call this free convection. Right? It's free because it's not being forced by anything external. It's just kind of happening just naturally as the fluid kind of heats up and cools down on its own. Okay. Any questions on this? Yeah. That's a good point. So the picture that I've drawn you here is a little bit inaccurate, and so they're not kind of forming a circle like this. It is kind of a bit more random. So if you think about if you boil a pot of water, right? You see water that's kind of the bubbles kind of floating up. It always happens in kind of a random way. So that's kind of a more accurate way to describe it. But yeah, so it's not actually circulating like that. It's kind of doing more kind of random stuff. Yeah.
Does this add any translational motion along the sea?
It does not. No. So it only goes on whichever direction gravity is flowing. So it's only going up or down. Yeah. Yeah. Maybe a little bit. But maybe as bubbles kind of crash into each other, they might kind of move a little bit left and right, but it's not. There's no net movement in the sea direction. It's only just up or down.
Is there another example of this free convection?
You actually see a lot of it in kind of industrial applications. Whenever you have kind of a very large surface that's vertical, we'll talk about this in a bit, then, you know, it's naturally going to heat all the air that's around it. Or you might see it in kind of deep sea applications as well. So when you have a big piece of machinery that's underground, like some kind of drilling rig or something like that, then that's going to cause density differences within the surrounding fluid. And it's going to cause something to flow. Yeah. Mm-hmm. Okay, so let me draw you kind of a similar situation, and let's see if we're going to have convection. Okay, and so on the above we have a hot plate on the bottom and a cold plate on top. And so let's reverse this. So let's have a hot plate on top and a cold plate on the bottom. All right. And so in this situation, do you think we're going to have any free convection? Right. So here, you know, the roles are swapped, right? And so the hot air up here is going to want to go up, but there's nowhere for it to go because it's bound by the hot plate on top. Whereas the cool fluid is going to want to go to the bottom, but there's nowhere for it to go because it hits the plate, right? And so here, there's no flow. No flow and therefore no convection. So you might have conduction, and so you might have conduction that's occurring, but there's no convection because there's no flow. So that's something to remember, you know, as we're going about this unit, is that you have to kind of always pay attention to which direction gravity is going to go and which direction the fluid wants to flow. Okay. And so you should always kind of be thinking about that, you know, which way is gravity flowing and which direction does the hot fluid want to go? Okay. Okay. And so I think a fair question to ask is, you know, how significant are these? Okay. And by that, I mean, you know, if you have a situation where you have both free convection and forced convection, how significant is that? Okay. And to kind of motivate that question, let me bring up our external convection case like before, right? And so let's say you just have a single plate here, right? You have flow that's hitting it, okay? So we have U infinity, T infinity, and our plate here is at a surface temperature Ts, okay? If Ts is greater than T infinity, right? Then what's going to happen, right? So the fluid near the wall is going to be heated up, and so it's going to want to rise through buoyancy, right? And so since the fluid is going to rise, the density differences are going to cause some kind of flow, right? And so here, you are going to have free convection, right? So that's not deniable. And so, you are going to get some kind of free convection. But at the same time, you have the actual fluid that's kind of flowing over the top, whether through pressure differences or something like that, okay? Right, and so there's a question. So, here we have a situation where we have both external convection and free convection, right? Right. And so the question we want to answer is, how significant is the free convection, right? Is it more significant than the external one? Is it less significant? Is it gonna change your answers quite a bit? Okay. The answer to this is that usually free convection is fairly small. And so usually if you have a situation where you have both external convection and free convection, usually the external convection will dominate. Okay. And so that's kind of the reason why we've kind of ignored it up to this point. And so if you compare, forced convection to free convection, the forced convection will almost always be greater. Okay. And so, that's kind of why, I've kind of saved this one for almost last, is because, it's the lowest of the three. Okay. But that doesn't mean we can ignore it sometimes. And so, there are situations in practice when the forced convection just is naturally very low. Okay. Or the temperature differences between the surface and the fluid are very, very large. Okay. Okay. And so in those situations, the free convection becomes a lot more significant. Okay. And in fact, engineers actually, free convection is usually a good thing more than a bad thing. So a lot of people kind of see it as like free cooling. And so that's another why it's called free, right? And so it's actual convection cooling that you don't have to do anything extra to do. Okay. And so in a lot of situations, engineers actually make use of this. And so they design their geometries, or they design their devices to take as much advantage of free convection as possible. So they have to spend less money on cooling. Okay. Yeah. And so, if you have a device that's in air or it's in water and it's heating up, right? That's free real estate. It's free convection for your device that you don't have to do anything for. And so some applications, we've already kind of talked about a couple of where free convection is big. One of those would be in kind of like any kind of deep sea kind of venture. Okay, just because you have very long lengths, and usually those in the water, ocean water is very cool. Okay, and so you have kind of free convection from that. It's also very common in any kind of power generation, and so any device that's designed to generate power. Okay. And also in HVAC as well. So if you work in heating, ventilation, air conditioning, free convection is something that you kind of leverage in your designs as well. Okay. All right, any questions on this? Okay, so let's so that's kind of our introduction to free convection. And so let's go ahead and talk about the situation that we're going to be dealing with the most. Okay. And so, because, free convection is kind of limited to just a vertical condition, we're going to look at kind of a very specific situation of a vertical plate. Okay. All right, so our plate is going to be vertical just like that. Okay. And so we have TS. And outside of the plate, we're going to assume that we have no velocity. And so outside, the flow is still. Okay. Or you can say that there's no flow. Okay, but if TS is greater than T infinity, right? And so our surface temperature is greater than our fluid temperature, then this is going to cause the fluid to move upwards, right? Because the fluid next to the plate is heating up, and so that's going to cause it to move forward, okay? And what you're actually going to see is some kind of boundary layer that actually forms, okay? And so because of the moving fluid and because of the boundary layer, we're going to have some convection heat transfer. Okay. Okay. And so I know we're just about out of time, but I do want to go over one more point. Okay. And so the nature of free convection is quite different than forced convection. Okay. And so in forced convection, the one of the primary numbers that we looked at was the Reynolds number. But in free convection, we're not going to use the Reynolds number because the nature of the flow is very different. Okay. And so instead of Reynolds number, we're going to use a new number called the Grashof number. And so the Grashof number, so we'll call that GR. I won't give you the expression yet because I want to kind of motivate that, but I do want to give you what it represents. Okay. So remember, most of our non-dimensional numbers here are some kind of ratio of some kind. And so the Grashof number is no exception. And so the Grashof number is a ratio of the buoyant forces inside of a fluid compared to the viscous forces. And so what you'll see in our analysis of our neutral numbers is that instead of Reynolds number is going to be replaced by this Grashof number instead. Okay. And that's going to help us compute our neutral number and then eventually compute our convection coefficients. All right. Any final questions on this before we wrap it up for spring break? Okay, so have a great spring break, everyone. Remember, homework's due Friday, but after that, I'm not going to assign a homework until after the spring break. So hope everyone has a restful spring break. I'll be available via email, so I'm not really going anywhere over spring break. So you can email me about anything over spring break. And I will see you guys after the break. Thank you, everybody. Yep.
The last problem to the model.
Yep.
Is that really on paper?
No, you have to do it. through MATLAB. And so what I want you to do is I want you to change the values and then observe how it changes the MATLAB. And then keep tinkering with the numbers.
That's what I was thinking.
Yeah.
And one of the so I can to basketball, what we learned
It's, I mean, you can, I mean, you're definitely gonna learn it.
yeah.
It is a little bit of a niche software, and so I think most companies won't know. And it's mostly used in research work. And so you might have to kind of explain skills.
Yeah, that's what I was thinking.
Yeah. Yeah, so I think the skill that's actually transferable is actually modeling and also the CFD seven. You can use it as like experience.
All right. That's great. Thank you.
Yeah. What's up? Sure. And I can maybe look up. I want to say, I don't think it's happening. I would ask. It sounds familiar. I'm not sure.
Use like some light and like some mirrors or stuff to like visualize the